In this video, we're going to determine the velocity vector of someone riding on a Costa Rican zipline. So we're told that the zipline is 1,000 feet long. It starts on a platform that's 500 feet high, 500 feet above the ground. The total drop over the entire 1,000-foot line is 50 feet, and the average speed of the rider is about 60 miles per hour. And in relation to a base camp, you can think about located on the ground, maybe around this location. We're given the coordinates of the start and end platform. So the ground level is at z is equal to 0. You could think about something like this. This is the x direction. This is the y direction. This is all parallel to the ground. And then z would be straight up and down. Again, I know we're above the trees here, but just imagine this is ground level. This origin point is ground level. And x and y are parallel to ground level, and z is perpendicular. Okay, so 1,000 feet long zip line starts at 500 feet high, drops 50 feet, which is about a 5% slope, 5 feet of drop per every 100 feet. So it ends at 450 feet high. Okay, average velocity of 60 miles per hour. Okay, and the starting coordinates are 450, 225, 500. This is in feet. And the ending coordinates are minus 415, minus 275, 450. Okay, now you might be saying, well, wait a minute. The zip line's not going to be straight. It's going to be curved. It's sagging. Well, there are functions that you can use to model hanging cables. That's called a catenary, which is modeled using hyperbolic functions. Any hanging cable, weighted cable rope between points, like a telephone line, this is a catenary shape. Again, modeled with hyperbolic functions. You could do that. Use calculus, get the equation for the tangent line at all points along the curve. And then use that equation to get the unit vector in relation to the tangent line at all points on the curve. But here we're just keeping it simple, assuming a straight line. So we start somewhere up here and then end 50 feet down over here. And it's a straight line. Okay, and you might say, well, you're not always going to be going the same speed, 60 miles per hour. Well, come up with your own velocity function. A velocity as a function of position along the zip line. It could be a piecewise function. When you get into this region, you slow down. When you get into other regions, it's constant. When you get into other regions, you speed up. Again, piecewise based on the position along the line. But again, here we're just trying to keep it simple so you can get a feel for applying unit vectors. Okay, so the only information we really need here to get the velocity vector is the start and end coordinates and the average velocity. I just gave this extra information to kind of paint a picture of the zip line for you. So the zip line is something like this, with the base camp and coordinate system being something like this. Okay, so all we need to do is get a unit vector that's pointing in the direction of the zip line. So since we know that this is the start and this is the end, so we just need a unit vector pointing in this direction. Because if we have that, then all we need to do is multiply the unit vector by the average velocity magnitude, 60 miles per hour, and that will just scale up the vector to a value of 60 miles per hour in the correct direction. So how do we get this unit vector, though, this v hat unit vector? Well, if we can just get the displacement vector from S to E, then all we need to do is just divide that displacement vector by its magnitude, which will result in a unit vector in the direction from S to E. So to get the displacement vector from S to E, we use the position vector of S and the position vector of E. Okay, so we can see that based on tip-to-tail vector addition, that the position vector of S plus the displacement vector from S to E is equal to the position vector of point E. Okay, so the displacement vector from S to E is equal to the position vector of E minus the position vector of S. So let's subtract these two position vectors. Here's the components of the position vector of S. Here's the components of the position vector of E. So what we have is we start with position vector E, so minus 415 I hat minus 275 j hat plus 450 k hat. Okay, now we're subtracting that from 450 I hat plus 225 j hat plus 500 k hat. Okay, so distributing the minus. Okay, so combining like terms, we've got minus 415 minus 450 minus 865. Okay, minus 275 minus 225 minus 500. And then 450 minus 500 is minus 50. Okay, so there is the displacement vector from S to E. Okay, so we know that this vector is in the exact direction that we're looking for. Even the sense of it is correct. It's pointing along the zip line with sense pointing towards the end. Okay, but the only issue is that this is not a unit vector. So to make this a unit vector, we just need to divide this by its magnitude. So what is the magnitude of this displacement vector? Well, that's just going to be minus 865 squared plus minus 500 squared plus minus 50 squared. Okay, so 865 squared so just add these. And then let's get this 100.36. Okay, so V hat is equal to this displacement vector divided by the magnitude of the displacement vector. So minus 865 divided by this. So minus 0.865 . . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 . 0.865 I hat, okay, minus 500 divided by the magnitude, minus 0.5 j hat, and then minus 50 minus 0.05. And there we go. There is V hat. Okay, this is a unit vector. It seems like it wouldn't be. Look at these random components, but 0.865 squared plus 0.5 squared plus 0.05 squared. Take the square root of that. 1. Okay, and it's pointing in the direction from along the zip line from the start to the platform to the end platform. So now all we need to do is just multiply this unit vector by the average velocity. It's just going to, since it's a scalar multiplication, it's just going to scale the vector up in the same direction. So it's just the velocity vector is equal to this V average times V hat. So you have 60 miles per hour, so times minus 0.865 minus 51.9. Okay, 0.5 times 60 is going to be 30, so minus 30 j hat, and then 0.05 times 60, and then minus 3 k hat. And there it is. And what's interesting is you can see how fast you're dropping. It's like a 3 mile per hour free fall. Okay, this is how fast you're moving in the X, Y, and Z directions, or relative to the base camp, with the magnitude of this velocity being 60 miles per hour.